So we'll start with week 9 first. So we'll go through the basic terminology for week 9, which is first thing is I'll just write down the terms first. Local maxima and local minima. And then there is turning points. Then you have critical points. Ideally, we should discuss critical points first. Critical points and then saddle points, which are also called point of inflection. So I won't write down the definitions of all of them. You just quickly discuss them. So starting off with critical points first. Wherever your f dash 0 becomes 0, the point where your f dash, let's just call this point A. Wherever your f dash becomes 0, that point is called a critical point. So either it's not it's 0 there, or you can say that f is not differentiable at A. F is if either of the two is happening, then we can say that it's a critical point. Then about local maxima and local minimum. So graphically, if you look at it, it's like this thing where you point of maxima, local maxima.
Ma'am,
is the-
screen is not sharing.
My screen is not visible, or is there any other problem?
It is visible for me. It is visible, ma'am.
Be visible.
Ma'am, your skin is visible, but your voice is a little bit low, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, ma'am.
Is there any other problem?
No, ma'am.
Okay. So this is typically called the local maxima, and when you have something like this, so this thing is called the local minima. So for this, what we do is we just see if your f dash uh, at some point is, let's just say it's greater than 0, then it's a local maxima, and otherwise, if it's less than discuss local maxima and local minima, you try the second derivative. So this is this just tells you that this is either a local maxima or local minima. It's basically this is for critical points. This is, let me just number these things. This is first. This is first. First. This is for your critical points, and then for your local maxima minima, if this thing is greater than 0, then it's a local minima. And, if this thing is less than 0, it's a local maxima. And then we have a distinction between local and global things. Local and global. So local basically means that in some intervals, basically this means that you will find some interval in which this thing will be the maximum. So if you see something like this, this graph, this is a local maxima. This is also a local maxima. This is a local maxima as well, because there is an interval in which this is the maximum value. This is also local maxima. But the global maxima is this thing. So this is the global maxima. That's the difference between local and global maxima.
Excuse me, ma'am. Your voice is actually too low and not that clear.
Yes, ma'am, same problem.
Okay, is it better now?
Yes,
Can
ma'am.
you hear me now? Is it better?
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay.
Yes,
So
ma'am.
what we're discussing is we've done critical points, local maxima minima, and then global maxima minima, and then we have saddle points and points of inflection. So for point of inflection, you have so if you see something like if you see that if your f dash a is actually 0, but then so it's something of this form. If it if it was increasing before and it was increasing still after that point. So if this is a point of inflection, then it remains. So what happens in a local maxima, minima, or global maxima, minima for that matter is you first go up and then you go down. That's the difference. First it's increasing and then it's decreasing. When the point of inflection, it keeps either it keeps increasing or it keeps. So that's your point of inflection. How do you check it? So if you see that, so if before the point you see that your f dash a is, let's just say, so you know how to check the increasing decreasing thing, right? So if before this point, let's just say f dash x is greater than 0, for x less than a, and for x greater than a, it's still less than 0. Sorry, greater than 0. Then we say that these both are x. Then we say that your a is a point of inflection because it's not actually changing the increasing to decreasing or decreasing to increasing. So this is called a
Ma'am,
point
it
of
is also
inflection.
called a saddle point.
Yeah, I've written it. Saddle point or point of inflection.
Okay, ma'am.
And then concave up, concave down is another concept. So for concave up, basically, if you concave up is basically this. Do we have concave up and concave down in syllabus? So this is called concave up thing, something like this, and then this is called concave down thing. The concavity that you check by the double derivative, which is if you have this thing greater than 0, then it's concave up. In an interval, you should rather say in an interval. So obviously, if you have a minima somewhere, you have a concave up. If you have a minima somewhere, you have concave up. If you have a maxima somewhere, you have wherever the maxima is, you have a concave down. That's what it is. And then, and in case we discuss two things here, right? And if you see this thing being 0, then the test is said to be inconclusive. That means you can't conclude anything from here. So you have to test for other things, but you won't see something like this. And then next up we have and one important point here is that
Hello, ma'am.
while
I'm
finding
really
local
sorry to
maxima and
bother
minima,
you, ma'am. Ma'am, what you discussed right now, can you summarize again, please?
we've not discussed much. We've just discussed the basic terminology for this. It's just critical points, saddle points, local maxima minima, and global maxima minima. That's all. We haven't discussed anything important yet.
Okay, thank you.
So for finding local maxima minima, in case you're asked, or for global maxima minima, you will need to check local maxima minima. You should be checking at the endpoints. Don't forget the endpoints. If they're included in the interval, that means if you've been given some sort of interval like this, then you should be checking at the endpoints. So to find local maxima minima, one thing is you check where the first derivative becomes 0. That's one point where you check all the points where the first derivative becomes 0. And then at the end points you check. That's where you check to find the local, and then you see where you get the maximum value or minimum value. That's the local maximum minimum. Then next up we have Riemann sum. So
What about the saddle points?
we've discussed that's the point of inflection only. Saddle points are points of inflection only. Saddle points are basically where we discussed this, right? Where your function either keeps increasing before and after the point or it keeps decreasing. Is it fine? Then we have Riemann sum. So for Riemann sum, first we discuss the partitions. What are the partitions of a given interval? So let's just say you've been given an interval A and B. So the partitions of it are basically, you can just partition it in. This is basically called the partition. So you just divide it into parts, and then that's called the partition. And that division could be anything. We don't have a rule for it. And the lengths of these intervals can either be equal or they can be distinct. So that's called a partition of it, and generally denoted by this x naught and then x.
Hello, excuse me, ma'am.
Your voice is actually getting jittery. I don't know whether it's getting low. Others also experience the same thing. I'm not sure.
Okay, so I'm trying to speak a little louder, but if it's still feeble, then
Yeah, I mean, now to talk is fine, but over the time it's getting gradually getting low.
okay. I'll
Sorry
try
for
to
that.
speak louder then.
Ma'am, I have sent just one doubt on the chat. Could you please take it? Actually, a conceptual error is happening.
Can we take up your doubt after we discuss week 9? Is it from week 9?
It is probably from week 10 or week 11. Just a conceptual doubt.
We're discussing week 9 right now. It's not. It won't be feasible for me to discuss week 10 and 11 right now. We'll take that up when we'll discuss that thing. Okay. We're doing the partitions. Then this is called the partition. Partition is basically this thing: x naught, x1, x2, and so on x. And this collection is your partition. And then the Riemann sum is, so basically whenever you have a function, the Riemann sum you discuss is, let's just say that this is your function x and this is the interval that you're considering. And then you divide it into partitions. So the partition is generally given to you. So almost all the times you've been given the partition.
Excuse me, ma'am.
Yes.
Is it necessary that the partition will divide the whole interval into equal intervals, or unequal intervals may also be there? But I
So I
sometimes.
just discussed a partition could be anything. It could be anything. It doesn't have to be, the intervals don't have to be equal. They can be unequal and they can be in any number. So you don't have to have a fixed number here either. They can be 10 elements here or 20 elements, or the intervals can be unequal. It could
Okay,
be
means
this.
just a sequence of points which divides the whole interval into any n parts.
Yes.
Am I right?
Yes, you're right.
Okay, thank you.
Okay, so this is this thing. So what you do in the Riemann sum, so Riemann sum basically depends on the partition, and the other thing it depends on is the point that you're choosing from each interval. So if this is an interval given to you, then either you will be given the point that you should be taking, or you can just, because corresponding to every interval you get a different Riemann sum, and corresponding to, so let's just say that your intervals are fixed now. This is one interval, the second one, and then third one, and so on. Still your Riemann sum is not fixed. So Riemann sum is something based, is this. If we define it mathematically, it's this thing fxi and then delta x. Delta xi is where your I varies from 0 to n minus 1. This is it. So where your delta xi is xi minus xi minus 1. So this is just the length of the given interval. So it's the length of this interval. And this fxi is basically the point that you're choosing. So let's just say this xi star, we should call it. Xi star is any random point from the first interval. So from the ith interval. So let's just say if you have fx1 star, it's basically x1 star is basically a point here. X1 star. And then you have a point somewhere here, x2 star. These points are also given to you. And so all you do is you just take the value of the function at this given point that has been given to you, the fixed point in the given interval, and then you take the length of this interval. So the length of this interval multiplied with fx1 star, the point that you're fixing, this thing it is. And then you just sum them up. So it's basically, if you have, let's just say you have only 3 points, x1, x2, x3, so it will be fx1 star, and then x1 minus x0, and then fx2 star, x2 minus x0.
Excuse me, ma'am.
And then yes.
The xi star, could you please again tell? Actually, I mixed up. Xi star, how is used to take?
Xi star is given to you in the question. So this thing will be given to you, and we'll discuss a particular type of sum as they are called the left Riemann sum, right Riemann sum, And then there is something called for the center as well. I don't remember the name right now, but there's one for center as well, where you take the middle point. So we'll discuss the specific cases, but for now we can just take any point. So if you
So
change the
generally
point,
it is given in the question, unless it is LRS
it's given in the
RRS.
question. Otherwise,
Okay.
there'll be infinite number of Riemann schemes.
Okay, okay.
For every partition, you have infinite number of Riemann schemes, unless you have not been specified the points to be taken from each interval. So this is it. Where fx1 star, x1 star is the point that you're choosing from interval. So this from first interval it's x1 star, from second interval it's x2 star. Then this is the height of the function. So basically this is fx1 star. This is it. And then your left Riemann sum is basically when you choose this point, the left point from each interval. So when you take xi star to be the left point from each interval, it's the left Riemann sum. If you take it to be the right one, it's the right Riemann sum. And if you take it to be the center of the interval, it's called something. It's not, I don't remember the name exactly, but there's one in your assignments. There's one question on it. And then you have antiderivatives. So next up we have antiderivative things, which are also called indefinite integrals. So antiderivatives are basically your f. So antiderivative of, let's just say we're discussing the antiderivative of f. So it's basically a function capital F, so that f dash x is equal to your small f. This is called the antiderivative of small f. So if this happens, you say f is antiderivative of small f. And then you can write this thing as, in an alternative manner, you can write this thing as this. The notation for it. It's also called the integral, indefinite integral. And then there are definite integrals where you take the finite values here. And if it's, when you take finite values here, it becomes something like this.
Ma'am, may I
Value
ask
is
a
called a definite
question?
integral. Yes.
Ma'am, if we have to solve this Riemann sum by dividing it into n intervals and then later on n tends to infinity. So, ma'am, will it give the same answer if we just do the integral?
If you have, there's something called Riemann integrable, and so when you do this thing, you get, if all of these are Riemann sums, right? And then there's something called Riemann integral. So if you calculate the limit n tending to infinity, and that turns out to be a specific number. So that if this is a Riemann integrable function, then the thing that you get from here, integration thing, and the one that you calculated from here for n tending to infinity, those are going to be same if it's a Riemann integrable function. Otherwise,
Okay. Okay, ma'am. Otherwise, it may give a different answer.
yeah, but then it's not Riemann integrable then. So you won't be able to integrate it here in the first place.
Oh, okay, okay.
But that's not there in your course, I guess.
Okay.
Is it?
Sir, ma'am, I'm not aware.
Okay. So
Means
yeah,
if n tends to infinity, then the answer would be same. Is
what
it,
you
ma'am?
do
That
here is you, okay, give me a minute. When you have, is Riemann integration there though in the course?
No, ma'am.
It's not there. You just have Riemann sums.
Yes, ma'am. But ma'am, we are facing questions where the area is divided into n parts and then n tends to infinity, and then we have to find the ith term, take the summation, and then find the
Yeah, that's fine.
answer. Yes, ma'am. Actually, I'm finding problem in creating the ith term for left and right Riemann. So if you have time, maybe you can include that.
Yeah, we can do a question on that if you want to right now.
Okay, ma'am. Thank you. Ma'am, I don't have a question because the question I got stuck, that's a part of the mock and we have not submitted.
I'll look for a question then first. Okay, so there's been given one question here. This is a very simple one, a trivial one, where they've taken just x. And then the interval they've taken to be this.
Okay, ma'am.
Just 1 second, let me read the question. And your xi is given to be I into 5 by n. So you keep the n as is. So let's just say you're dividing into 0, 5 into n parts, right? So your first x naught will be 0. And then you have x1 equals 1 into 5 by n. So this will be 5 by n.
Yes, ma'am.
Then your x2 will be n
So
by
2
n.
times. Yes, 2 into 5 by n. Yes.
And then you keep going on like this. And finally, you'll have 5n by n. So you'll just get 5 here. It's 5n by n. What you do here is you, and the point that has to be taken is what type of questions are there though? I don't remember right now.
Ma'am, same kind of. And then we have to create the ith term. And then summation and n tends to infinity. That's all.
Okay, so you have not been given xi star, that's why. So and you've not even, so what you might be asked to do is you will be asked to do the left Riemann sum and right Riemann sum in this one, as far as I remember. So what you do here is you take first for the left Riemann sum, you take 0 there. So you do f0, and then this interval's length is 5. So all of them's length is like 5 by n only. So you can just take 5 by n to be right.
Yes, ma'am.
5 by n, this is 5 by n. Then you'll have f at 0, then f at 5 by n, because it's a left Riemann sum, so on, so on. And then you have f at 5n minus 1 by n, right?
Ma'am, second point will be okay, 5 by n. Yes, ma'am, correct. Yes.
So you'll have this thing. And then
Ma'am,
at f0, you have,
what is the last term, ma'am? Last, yes.
this is 5n by n. So going by the pattern, this will be this, right? Minus 1 by n.
Yes.
So f0 is 0, then f5 by n will be 5 by n. So we'll have the same things. This will be 10 by n. And then you just take the sum of this. So this is basically 5 being taken common, and you'll have, let's just take n common too. You'll have 1 plus 2 plus 3 plus so on till n minus 1, right? And then you just add this. So the sum is, I guess, n minus 1 it is, right? Or is it n plus 1? The sum for first n terms.
First n terms, ma'am, n plus 1 by 2.
Okay, so this is have n minus 1 here, and then so you're still going to get the same thing here. Doesn't matter. This is what you're going to get, and then you just take the limit of this. So you'll get this. And there you'll get 25 by 2, 1 minus 1 by n. So if this goes to infinity, this will just be 25 by 2. Similarly, you calculate the right Riemann sum. And if both of them turn out to be same, yes.
Ma'am, here I'm finding it difficult how this n minus 1 by 2 you have calculated, because I mean, I'm not very good with series, but the first n terms is n plus 1 by 2. And here we have n minus 1 terms.
Right. So the formula for the sum of first n terms is n plus 1 by 2. So if you take first n minus 1 terms, you'll have n minus
Okay.
1, n minus
Into
1
n.
plus 1.
Okay,
Right.
okay.
So you still get the same thing.
Okay. Okay,
Thing
ma'am. Okay,
only.
okay. Correct, ma'am. Thank you, ma'am.
Okay. Then, so you in your graded assignment and the solve with us part, you have been given the important integrals that you should know. There's a list of integrals that you should know. So you can just go through them from there. And because we don't have enough time to discuss them here.
Yes, okay, ma'am.
And do we need to do some integrals here as to how to do integrals? I can just
Ma'am, here in Riemann, can you also tell how to do the right Riemann? Because this is the left. So
in right one, you just take instead of, so in left one, what you do is you take these points. From this interval, you take this point. From this interval, you take this point. In left Riemann sum, from this interval, you take this one. Then from this interval, you take this one. So in the sums here, you'll get from 5 by n to 5. You get this thing here. Is that okay?
yes, ma'am, the nth term will become 5n by n. And we'll do the same here. Okay, ma'am. Thank you, ma'am.
Ma'am,
Yes.
Can
ma'am,
you
there
repeat
was
this
something
integral?
called ma'am, there was something called norm of P. Can you please explain that?
Okay, norm of P is basically the partition that you have. This thing it is x0, x1, and so on, xn. If you say this was A, this was B, this was an interval A to B, and this is your partition. So your norm of P is basically the maximum of the length of these intervals. So maximum of length of xi to xi minus 1. Is this okay? It's simply this might confuse you. It's simply the length, the maximum of these lengths. This length and then x2 to x1 length, and then x3 to x2 length, and then so on. You take all the lengths here of each interval, and then you take the maximum of it. That's the norm of P.
Okay.
And then there's one thing that helps a lot in doing integrals. So I'll just write down the formula for it. So it's this thing, but let's just say that you've been given composition of functions. Sometimes you've been given a complicated composition of something. And if you see something like this is basically f of gx. And then this is multiplied with g dash x. So what you can do here is you can just substitute gx equals to some t variable. So this will become ft. And then you take the derivative of both of these things with respect to. Because what you want is when you replace gx with t, you want everything in terms of t. You want to replace x from here. So you're substituting t in place of gx. So we just take the derivative of both of these. We get g dash x, and here you get dt by dx, but it becomes this. So you can replace g dash x dx with a dt. This is how you do the substitution. For example, let's just say you've been given sine x. You've been given the integration of tan x, let's say. What you do is you write it as sine x by cos x dx, and then you substitute this thing as t. So here you get a t, and then sine x dx becomes cos x
dt.
derivative becomes minus dt. Minus because cos's derivative is minus sign, right? So this becomes minus dt. And then this becomes log of t because 1 by t is input, and this is it. And then you replace t back with the cos x. So you get log of cos x minus. Or if you want, you can write it as log of secant x. That works too. This is one example of doing the substitution thing.
Ma'am,
And then
here
you
you
have
written
limits here. Yes, one more point that I'd like to clarify. When you have limits here, please don't forget to change the limits here. If you have something, say, from minus pi to pi, just say you had 0 to pi here. So how do you change it? You know that your cos x is t. You've substituted cos x equals t. So you put x equals to 0 here, you get t. So at x equals to 0, you get t equals to 1. And at x equals to pi, you get t equals to, so cos pi is minus 1, right? This is
-1.
So the limit becomes from it changes from 1 to minus 1. 1 to minus 1.
Ma'am, cannot we just substitute first and then we apply the limit?
Which limit?
Ma'am, suppose this original limit was given 0 to pi. And then we
Okay.
have done the substitution. Finally, we got the answer minus log mod of cos x.
Yeah, that's what you need to change. In the beginning, when we were doing this thing, we didn't have a limit here. So the answer was simply this thing. But I was just trying to tell you that if you do see limits here, then you will need to change the limits here as
No, ma'am, my question is, suppose I don't change the limit and I get the final answer, I substitute. And now if I apply the original limits, will it work?
I mean, yeah, if you see, you won't have to. What I was trying to say is, if you do all of this work, so your final answer is this. You can just apply the limits, right? You don't have to
Yes.
do all of this.
Okay.
So you
Okay.
don't have to go to this part. So if you're going till this part, you can use these limits. Otherwise, if you don't want to do all of this substitution, you can just put the limits there.
Okay. Okay, ma'am. Thank you, ma'am.
And then we've discussed some trigonometric formulas that might help you in the integration things in the lecture itself, in the summary part. So you can go through that from there. And then we'll start with week 10 now. Before that, anyone who has a doubt from week 9, if there's anything that you feel is not yet discussed, you can just ask.
Ma'am, I want to know what do we do with norm of P? I mean, it's okay, it's a maximum of the interval, that's good. But then what do we do? Like, what is the use of it in our syllabus?
It's not, you don't use it in your, I don't think there's a use in your syllabus from where I see, but it's used in Riemann integrals actually.
Okay, okay, ma'am.
Start with graph theory then. In graph theory, so I'm not discussing from the very basics. I'm not discussing what a graph is, what a directed graph is. I hope you know these terms. If anyone, uh, I'm just telling the terms here, and if anyone who's not familiar with these terms can ask, and I'll just tell what it is. So there are graphs, edges, vertices, and then we have directed, undirected graphs. So I hope all of you are aware of what all these terms are. Then we have a path and an edge. So we'll directly come to the applications of graphs, some major applications of it. The first that we have is graph coloring problem. So graph coloring problem, you have been given vertices, and then what you do is you just need to, so looking at the graph, you just need to decide minimum number of colors that you can use to fill these vertices such that no two adjacent vertices have the same color. That's what graph coloring problem is essentially. So I'll just repeat it. You just color these vertices in such a manner that no two adjacent vertices have the same color. So in this one, what if you have say this thing, so you need a color for this one color, and then you need a distinct color for this, and you can keep. So you can't take two here and one here because this thing is adjacent to both of these. So you need a different color here. and then you can either choose 2 or 3. Any one works. So with 3 colors, you'll at least need 3 colors for this one. That's a graph coloring problem. And then second, you have vertex cover.
Ma'am,
Yes,
if we start from different nodes, will the answer be different in graph coloring problem?
no, it will be the same.
Okay, ma'am.
You can choose whatever vertex you want to start with.
Ma'am, can you tell which is not and which is edge, ma'am? I'm always confused in these two terms.
Sorry, which is an edge?
And which is an nodes, ma'am?
Nodes are basically vertices only. So these are called either vertices or nodes. And these things are edges.
Yes, ma'am. Thank you, ma'am.
Okay. And then you have vertex cover problem. So I'm not discussing the application and all of it because we've discussed it in detail in the lectures, that the summary part of it. So you can go check it from there. We just quickly go through all of these applications, the applications of graph theory. Vertex cover is basically, so when you have a graph, let's just say this is a graph. So in a vertex cover problem, what you want is from each edge. So if this is an edge, you would want from each edge there should be vertex cover is basically the, so this, if this is set of vertices, then vertex cover is basically a subset of set of vertices where you collect the vertices in such a manner that from each edge you have at least one vertex. Let's just say this is first vertex, second, third, fourth, fifth, and sixth. So you choose this edge first, then you pick any one of these two, and then from this one, it would have been easier if you would have chosen 2, because 2 will cover all of this. It will cover this thing, and this thing. So it will cover all the edges. So you should choose 2 here, because 2 covers this edge, and this edge. And then you don't have 3, so you'll have to take 4 for this edge, and then this is also covered. So this is your vertex cover in this example. Okay. Then next up we have independent set. So independent set is again a collection of vertices only. So how do you collect the vertices in this case? Let's just take this one only. We'll take this example only for the independent set as well. So you collect vertices in such a way that you don't choose the connected ones. Like if you're, let's just say we start with 1. So you can't choose 2, but you can have a 6 here, because 6 is not directly connected to 1. Directly connected as in 6 and 1 do not have a common edge. So you can take 6 here. Then you can take 3 here, because 3 and 1 do not have a common edge. And then you can take, now you can't take 4 because 3 and 4 have a common edge. And then you can take 5. So this is an independence. You just need to make sure that none of these have a common edge. That's all. That's your independence. If you start from, let's say, which one's missing here?
Can you
4 is
explain
missing here.
independent set once again?
Independent set is basically, it's a collection of vertices. What type of vertices do we collect here? We collect the vertices that do not have a common edge. We've chosen 1. So if we start with 1, we can't choose 2 because 1 and 2 share an edge. So we'll have to choose 6. So you put a 6 here. So this is independent set, and then you have something called maximal independent. These are 2 different things. This is a maximal independent set, and it's independent. Maximal independent set is basically the independent set, but you include all the vertices that makes it that keeps it independent. This is an independent set. If I remove a 5 here, it will remain an independent set, but it won't be a maximal independence. All right.
And
Ma'am,
what is
that
the
means
reason for 3 then?
which are not share edge.
Yeah, they should not. All of these, if you randomly choose any 2 of them, they should not share an edge. It's a simple piece.
Yeah, ma'am.
It must
And
not
if you
share
choose,
heads.
Yeah. Ma'am, it is maximal or maximum, ma'am?
maximal, it's maximal.
Ma'am, what is the difference between maximal and maximum?
Term uses maximal. There's no such thing as maximum independence.
So why maximal is used? Because
There's no reason for it. It's just terminology. You don't have to get into why it's called this thing and not the other thing.
Ma'am, what is
It's
the
just
reason for 3 then?
3, because 3, see, 1 and 6 are there. 3 does not have, why do you not, you start from here. Let's just say you start with a 1, and you see 1 and 2 share an edge, so you can't have 2 here. Just give me 1 second. Let's just say that you have 1, you start with 1, so you can't take 2 in the set because they have an edge. Then you will take 6 because 6 and 1 do not have an edge. Now you have 1 and 6, so you have to make sure the other vertex that does not have an edge with 1 and 6. 3 does not have an edge with 1, it doesn't have an edge with 6. Then you move on to 4, but 4 has an edge with 5 does not have an edge with any of the already mentioned ones, 1, 6, and 3. So you can include 5.
We took
So this becomes
3
the maximum.
because of 1 and 6 doesn't have edge and edge with 3.
Yeah.
We don't took 4 because of it has, we already took 3.
If you're just discussing, this is the maximal independent set. That's why it turns out to be like this. You start with a 4.
Ma'am,
You'll have,
ma'am, 2, 4, 6, if we take, it is also an independent set, no?
yeah, 2, 4, 6 is an independent set, but it's not the maximal one. 4 and 6.
2,
It's
4, and
fine
6.
too. Yeah, it's also maximal in the term that you can't include any other one. Yeah, that's fine too.
So both are
It's also
maximal
maximal
independent set, ma'am.
Yeah.
Or we
Ma'am,
can say,
is it necessary when we talk about independent set, we need to take the maximum independent set?
See, when we do practical questions on this, when we do questions on it, we generally need to find the maximum independence. Independent set is usually not needed to find. So you'll have to find this. This is what you will be asked to find. You won't directly be asked to find maximal independence set, but the question would imply you to find maximal independence set.
Okay,
We
ma'am.
discussed an example on this in the summary session. On each one of these, actually. Then we have something called matching and another term, perfect matching. So matching is basically, let's just say you have a graph here. So a matching would be, it's basically collection of edges such that no two edges have a common vertex. So till now we were collecting vertices, now we are collecting edges. So in a matching, you collect edges. What sort of edges? Let's just say we collect 1. Then we can't choose any other edge with vertex 2 included or 1 and 2. We can't choose 2 and 6. We can't choose 2 and 6, but we can choose 6 and 3. Then when 6 and 3 are already included, so we can't choose 6 and 4. We can't choose 6 and 5, so that's it. This is a matching.
6 and 2.
Is there a doubt? Can you explain this again? Matching is basically a collection of edges where no two edges share a common vertex. That's it. So if you've included 1, 2, you will have to, the only thing now, one other possible matching could be you take 1, 2, and then you take 6, 5 instead. This is a matching. Because you have 1, 2, 6, 5, they don't share a vertex. What?
Can you point the edge and vertex?
This is the edge 6, 5. This is the edge 1, 2. Is this fine? They're not directed. So when you take 1 to 2, if it's in this manner, you write it as 1, 2. You can't change the order. But this one is not directed edge. So you can either take 1, 2 or 2, 1. It's the same thing in an undirected graph. Is it fine now? And for a perfect matching, so this does not have a perfect matching. Why? Because let's just define what a perfect matching is. So This is a perfect matching where no two edges share a common vertex. And in a perfect matching, it's a matching that means the edges that you include should not share a common vertex. Plus, there's one more condition to it. So this is condition 1. And the second condition is that every vertex should be covered in the edges. Every vertex should be included. Included in the sense, now here when you see you don't have a 4 here. So 4 is missing from the set. That's why this is not a perfect matching. And this, by the way, does not have a perfect match. Because for you to include 4, you can only include it with 6. So if you include it with 6, you'll have 6, 4, but then you can't have 6. But if you have something like this, let's just say you change your graph to this. Now you can have a perfect matching as 1, 2, then 6, 5, and 3, 4. Now we do have a perfect matching. Is this okay?
So in perfect matching, every vertex should be covered, right?
Yes. Vertex should be covered and every vertex should be covered only once. So in each edge, if you have a 2 in one edge, you should not have an edge with 2. In
Can you
this
show that the graph works again?
Is there a doubt? Okay, then we're not discussing what an adjacency matrix is. So I'm just writing the terms here. And then you have degrees of vertices, in degree, out degree. And reachability. So if anyone has a doubt in any of these terms, then we can discuss it. Otherwise, we're not discussing it.
Ma'am, I don't know why, but I'm not getting it.
What are
Ma'am,
you not
in
getting?
degree,
Okay, does anyone have a doubt till this point?
Yes, ma'am. I'm not getting.
You're not getting what exactly do these two terms mean. Okay, so if you have some graph, you can have any graph. What you do in a matching is, so if you want to define it, it's basically the collection of edges. So you collect edges here. You know what an edge is, right? This is an edge, this is an edge, this is an edge.
What is
Out of all
what
these edges,
exactly, ma'am? What is happening here? BFS or DFS?
we're not doing DFS and BFS here. DFS and BFS is a separate topic.
It means just you are doing means like relation attaching. Just you are summarizing.
Yeah.
Okay.
So do I need to repeat what a matching and perfect matching is, or is it already clear to everyone?
Ma'am,
You
so
can-
perfect matching is
you
only
can
possible if they're like
exactly.
even numbers, right? Of
Yeah.
edges. Okay.
If you have even number of edges, if you have
Even number of vertices.
if you have even number of vertices, it doesn't depend on edges, depends on vertices actually. So if you have even number of vertices, you can't be sure that you will have a perfect matching. For example, in this one, when you had this initially. Now you have even number of vertices here, but you still don't have a perfect matching, right? Even number of vertices does not guarantee that you'll have a matching, but if you a perfect matching, but if you have a perfect matching, then there has to be even number of vertices. So to
Okay,
even talk
okay.
about a perfect matching, you need to have even number of vertices.
ma'am, perfect matching, that means all vertices are covered.
Yes, all vertices are covered and they're only covered once in each edge. So if 2 is covered here, you can't have an edge with 2 again here. Like in this one, if 2 is covered, you can't have 2 again.
Okay, ma'am, understand.
Okay. And there are these terms, adjacency matrix, degree of vertices based on the graphs that you have, and then in degree, out degree, and reachability. If anyone has a doubt in these terms, then we'll discuss it. Otherwise,
Ma'am, in degree and out degree.
okay. Degree and out degree. So you discuss in degree and out degree separately only when you have a directed graph. Let's just say you have a directed graph. Yeah. Let's just say you have this thing. So if you have these four vertices, then the in degree of one is basically the vertex 1. So in degree of vertex 1 is the edges pointing towards it. So since there is no edge pointing towards V1, then it's 0. And the out degree for V1 is 2 because there are two edges pointing out of it. So it has out degree 2. Similarly, you do for all the other vertices. Is it okay?
Yeah, ma'am. Okay.
Can you could you give me a very short and quick recap of reachability?
Okay, reachability is basically it's basically just an idea whether you can reach from a given vertex to a given other vertex. So let's just say you want to reach so from here you see that you can reach from V1 to V3, but you can't reach from V3 to V1, right? That's what reachability is. So if you have one vertex, all the other vertices that you can reach to is called the reachability. That's why I say it's an idea.
But reachability doesn't have anything to do with whether it's a directed or undirected graph, right?
No, it doesn't have to be a directed graph. You can have an undirected graph too.
Oh, thank
You can talk about reachability there too.
you. Thank you.
Okay. And
Can
then
you explain the degree?
just 1 second. And then we have another thing called adjacency list. We've discussed all these terms in the summary session, but degree is basically when you look at, so when you talk about directed graphs, you talk about in degree and out degree separately. When you have an undirected graph, say this one, so this is an undirected graph, V1, V2, V3, then the degree of V1 is 1, degree of V2 is 2, because it has two edges connected to it. It has two edges from V2 has two edges from it, and then degree of V3 is 1 again. Is it fine? So it's the number of edges that you have from a given vertex.
So, ma'am, V2, V3 also have 2, right?
V3 has 1 only, right? It's just connected to V2. It just has an edge with V2. It doesn't have an edge with V1.
Okay.
And then we have the
Ma'am, what is
Okay, so-
adjacency list?
adjacency list is basically it's this thing. So let's just say let's just consider this graph. So, or maybe this one's a better graph. So it's basically the collection of these things where you collect all the points that you can go to from V1. So if you have an edge from V1 to some point, then you collect it here. Like in this example, you have an edge from V1 to V2. So you can write V2 here in your list.
V4.
And then you have an edge from V1 to V4. So you can write V4 here. That's You can only go to 2 points, to V2 and V4 from V1. And then similarly, you do it for the other ones. For V2, you make the list. For V3, you make the list. So this collection is called adjacency list.
Okay, ma'am.
Okay. And then we'll discuss BFS and DFS approach. So in a BFS approach, BFS is basically breadth first search. And for it, you first okay, let's just have a graph first. Let's just say you have this thing. So in a BFS tree, what you do is obviously BFS is basically to find out the reachability from one vertex to some other vertex. So let's just say you want to find the reachability of V5 from V1 or from some other vertex to this from V1 or from one vertex to some other vertex. If you want to find the reachability, then one approach to it is BFS. So in a BFS approach, what you do is you want to start with, let's say, V1, and then you need to find all the vertices that are reachable from V1. So in this case, because it's an undirected, okay, so because this is an undirected graph, so we consider it to be from this to this as well, and from this side to this side as well. So we consider it both ways, right? Because we've not been given a direction. But let's just say if we take it with directions, then it will be better to discuss this thing. Let's just say these are the directions. Then it's more interesting to verify if you can reach from V1 to V5, or what other vertices can you reach from V1. If you start with V1, what other vertices can you reach from V1? So there's one way to do it is BFS, and then the other one is DFS. So in a DFS search, what you do is you collect all the vertices that are, this is called a queue, and you collect all the vertices that are directly connected to V1. So directly connected to, there's only one, V2. And then in next up in the queue, you collect the points that are directly connected to V2. V4 is directly connected to it. You have an edge from V4. So you just write V4 because there's no other edge pointing out of V2. So it's just V4. And from V4, okay, then let's just change the edges because we don't have to emphasize on the BFS approach. We need to at least two pointing out from there. So from V2, you have V4, and then you have V5 as well. So you connect V5 here. And then you go to V4. So the one that you entered first will be explored first. So you go to V4, and then you check if there is an edge pointing to out of V4. So V4 you just leave because you don't have a edge pointing out of V4. And then you go to V5. So V5 you have an edge here till V6. And then after V6, so because V5 is done, then next up is V6, then you write V3 here, this edge. Is this fine? It doesn't very clearly, okay, this thing doesn't very clearly emphasize on how are we using BFS approach. Let's just take some other example. Let's just say you have V1. Let's just say you have this thing. So here what you do is you make a queue. And let's just say you're starting your search from V1. So you write V1, and then you start exploring V1. So you go to V2, V3, and V4. V2, V3, and V4, you write here. Then you start with this one. So the one that you enter first here, you go one by one. So V1 is explored because every vertex that was directly connected to V1 has been visited. So this is done. So V1 is done. Then you go to V4, V2. And then in V2, next up is V3. So V3 is already here. You don't need to write V3 again. You don't repeat vertices in a queue. Then you go to V3. So V3, next you can write V5 because V5 directly has an edge with V3. Then you go to V4, and from V4 you go to V6. So this is it. That means each of them is reachable from V1. You started with V1 and each of them is reachable. And how do you make a tree out of it? So you have V1 and then you have 3 here, 3 directly connected to it, V2, V3, V4. And then
And V3 is
V2
not
ends here.
connecting V4, right?
Yeah, V3 is not connected to V4 directly. It doesn't have an edge with V4.
So why after V3, V4?
Because in a BFS approach, you first write V1. So you start with V1 and then you write all the vertices that has an edge with V1. So V2, V3, V4. And then you start with this one first, V2. So you
Ma'am,
go
we
to
go
V2.
sequence wise.
Yes, we go sequence wise in this order in BFS search.
Okay,
Then
ma'am.
you go to V2 and then you write V3. So V3 is already written here. You don't repeat vertices in a queue. So leave V3 here. V2 is explored because there is no other vertex connected to V2. Then you go to V3. Next is V3 in the queue. Then from V3 you go to V5. So you don't go from V4 to V5, you go from V3 to V5. So V5 is here because V3 is here.
Okay, V4 is already.
And then you don't start exploring V5. Let me just tell you, you don't start exploring V5. What you do is you go to V4, the next one. After you're done exploring V3, you go to V4 and then you explore V4 first. So V6 is here because V6 is directly connected to V4. That's why we have a V6. So if instead you had this thing, let's say, if you had this thing instead V7, then you would see V7 first here. And then you would see V6.
Okay.
Which
Ma'am,
vertex
can
was
you
this?
take a ma'am, can you get an example of agency metric then explain BFX by metric?
Just one second. Let me just make the BFS tree for this, and then we'll discuss the problem.
Okay.
So this is a BFS tree. Tree is basically okay. Let me just define what a tree is first. So, are you let me just write the terms, and then you can ask which terms are you not familiar with. You can read the terms, right? Is it legible what I'm writing?
Yeah. Tree and connected graphs.
So any term that's written here which you're not familiar with or which you have a doubt in, you can just ask. There are 4 terms here. What?
I'm fine with the terms, but in the previous this thing, the BFS graph, after V3 and V4, how the second layer will start?
We'll discuss BFS tree once everyone is clear with all these terms. I just need to
Oh,
make sure
okay.
that everyone knows what a tree is.
Okay, fine. Thank you.
Okay, so does everyone know what a tree is, what all these terms are? Otherwise, we'll discuss the terms.
Ma'am, tree and connected graph.
Okay, so connected graph is basically if you see that from one vertex, you can reach every other vertex, then it's a connected graph. So if from a given vertex, you can reach every other vertex, it's called a connected graph. Is this fine? As in
Okay,
this
ma'am.
one, you will have to check. You just check that you can visit every vertex from V1, right? So similarly, you will have to make sure that you can visit every other vertex from V2 and then from V3, and then you can say that it's a connected graph. So this is something in the directed case. Otherwise, when you have, let's say, undirected graph, let's say you have this thing, then we are very clear that this is a connected graph, right? Because every vertex, you can reach every vertex from every other vertex. But if you have this thing, let's just say, then it's not a connected graph because now you can't reach from this vertex to this vertex. That's a connected graph.
Ma'am, is tree a connected graph?
Yes, tree is a connected graph. It's a maximal connected graph. Sorry, minimal connected graph.
And what is the difference between maximum and minimal?
Minimal connected basic. Okay, let's just say you have this thing, right? Maximal connected is not needed, but I'll still tell what maximal connected means. But this is not a term in your syllabus. And let's just say you have this thing here. These all are vertices. These corners are vertices. So we know that this, and let's just say you have this thing. So a maximal connected, the maximal connected set is this. If you just have these two or these 3 points, if you just consider these 3 things, then this is a connected thing, right? This is connected, but it's not maximal connected. So maximal connected would be this whole thing, right?
All right.
Okay, but you don't need maximal. Maximal connected is not a term here. That's why I don't want you to remember it. Just forget it. You just need to remember minimal connected set, which is called a tree in short. A minimal connect. If you look at this thing, you don't need this edge, so you can remove one of these edges, right? If you remove this edge, it is still a connected set.
Yeah.
This is called a tree. So in this case, all in all, what you need to make sure in a tree is that it should be connected and it should not have any cycles. For that, you need to know what a cycle is. Do you know what a cycle is? So I hope everyone knows what a cycle is and what's an acyclic.
How we will understand by adjacent matrix this is a cycle or a cycle? Ma'am?
We'll discuss adjacent matrix in a while, but I just want to make sure everyone, we're discussing this right now, so everyone's clear with all these terms, right?
Ma'am, tree can be directed or undirected also, ma'am.
It can be anything.
Ma'am, if tree is
You
directed,
can
then
talk about
if tree is directed, then is it connected?
connected has nothing to do with directed, undirected. Connected simply means that you want to make sure that from a given vertex you can go to every other vertex via edges. That's all. You need a path from one vertex to every other vertex.
From every vertex, we can go to any other vertex.
Other vertex, right? If you can go from any vertex to any other vertex, then it's a connected graph.
Okay.
And the minimal connected graph is called a tree. That's all.
But ma'am, I have seen that in drawing of tree, you cannot go from every point to every other point.
So obviously, you can in a tree you can obviously. That's why it's a connected graph. Tree is it's not okay. It's a minimal connected graph, so it's obviously a connected graph.
Maybe if it is directed, then we cannot go from in the reverse direction.
That's not okay. You can't go in the reverse direction, but you can still go. All you want is that's why in a BFS tree you generally have directions there in a BFS tree. You're right in that sense that you can't go in the opposite direction, but you can still go from there to here, right? So yeah, in a you can in a way you can say that in a directed graph you can't go from every vertex to every other vertex, but you do have a path from a tree is basically okay, that's how you define it. It's a minimal connected set, but in a directed graph you can't go the other way, but it's still a tree. We'll discuss it in case of directed ones as well. Just give me a minute. So as in this case, when you discuss about BFS tree as we're discussing here, so you first I'll just make the tree and then we'll discuss from where we can go to where. So you go to all these three vertices and then from V2 you can go to V3. But V3 is already mentioned here. So you don't just make sure that when you're making a tree, there are no cycles. That's the one rule that you follow in making trees. That you need to avoid all the cycles that are there. So V2 and V3 cannot be connected because then it will be a cycle here. Or that's not even a cycle. It will just be there'll be an extra edge here. That's it. So you don't because V3 is already you can already reach V3 via V1, so you don't include V3 here. That's my point. So you don't write V3 separately here, or you don't connect V3 with V2 here. And then from V3 you can go to V5. From V4, okay, and we need to follow this thing, right? So first V1 was there, and then V2, V3, V4. Then we have V5, and here we were discussing something else here. We have V6 here. But V6 came via V4, so you write V6. So this will be the tree for this, the BFS tree. And about the connected disconnected thing. So just give me a second. In a directed graph also, you don't actually need to do the connected part here. All you need to make sure is that if you have, there shouldn't be any cycles included, and you should be able to collect all the vertices here that are connected to it, that you can reach through V1. Is that all right? But a connected graph is, in typical terms, a connected graph is only the graph from every vertex, in which from every vertex you can go to every other vertex in the graph. That's what the definition of connected graph says. Is it all right?
Yeah, ma'am, all right.
Okay, but in the BFS tree, so ideally you shouldn't be calling this a tree. This is a tree because if you can't go, you're not sure if you can go from B6 to B4, but this is called a BFS tree only. Okay.
Ma'am, can you explain acyclic graph?
A cyclic graph is a graph which does not have any cycles, and cycles are basically this thing. So this will be called a cycle in a directed graph, and in an undirected graph, this can be called a cycle. So in an undirected graph, any closed thing that you see is this is called a cycle in an undirected graph, and in an undirected graph, you need to follow the order of these. So if you, instead of this arrow, if you have an arrow from here to here, then it's not a cycle. This thing is not a cycle. That's a cycle, and when you see no cycles in a graph, it's called an acyclic graph.
No cycles like
We have
square being made.
we'll keep discussing very minor things. We just miss out on important things that are there. We'll start with DFS, depth first search. So in a depth first search, what you do is we'll just do it for this graph only. So in a depth first search, you have something similar, a structure that looks similar to Q, but it's called stack here. So in a stack, what you do is, so instead this time what you do is, okay, so when you start from here, let's just say you're starting your search from V1. So you write the V1 here first, and then you go to V2 next. And then from V2, just give me a minute. Okay, so you start with V1 and then next up, so in a breadth first search, what you used to do was you will first visit every vertex that is directly connected to V1. But that's not what you do here. First you go to V2 and then you stop looking up for this thing. So you don't do the breadth thing first, you go into the depth first. So you go to V2 and then you next up you go to V3. And then from V3 you go to V5. So, or just give me a minute. One second. Yes, so we were discussing the depth first search. So let's just do the depth first for this one. So you start with V1 and then you have V2. So next up, instead of going into the breadth, so I was saying instead of exploring the breadth first, you go into the depth first. So that means after V2, you'll go to V3 directly and then to V5 from here and then to V6 until you can't go anywhere. So from V6, you can't go anywhere. So you stop here. And then V1, and then you come back to, so V1, you'll come back to the last one. V6 is here, and then you come back to this last one, V5. So from V5, you could only go to V6, and there's no other place to go. Then you come back to V3. From V3, you can only go to V5, and no other place to go. So V5 also gets, it's like they're done. We have explored all of these. And then from V3, you go back to V2. So V2 is also something that's not connected to anything else. So this is also done. And then you go back to V1. And then you see that you can go to V3, but V3 is also already covered, so you don't write V3. And then you see you can go to V4. So you write V4 here. So you have V1 here, and then from V1 you went to V2. From there you went to V3, then V5, then V6, and then you come back to here and go to V4. So this is your depth first tree. Is this all right? Is this clear to everyone?
Ma'am, can you
Yes,
explain
ma'am.
another example?
Yes, ma'am. Yes, ma'am.
Which example?
Any other example you can take?
Okay. Let's just take something which is not very trivial. Let's just say you have V1 to V2, then V4. And then let's just say you have this thing and V3 and V5 here. And then you have V6 and V7 here, let's say. When you have this thing, and let's just say you're starting your search from V1. So let's just say you have this thing. So you start with a V1, then you do V2 here. You can choose any one of these two, but if you choose V2, then you follow V2. You forget V4. And then from V2, either you go to V5 or V3. So we again choose randomly one. We go to V. Let's just say we go to V3 first. V3, and then you will go to, now there are two connected to it. So you will go, let's just say I'm going to V6. I'm choosing to go to V6. And then I can't go any further from V6 because V6 is done now. So now you start tracing back from here. So you go back to V3 because V6 has nothing to visit. So you go back to V3. Then you see V3, you can visit V7 from here. So you write V7 here. And then you from V7 you go to V9. So after V7 you have V9 because you can go from here to there. And then you see there's nothing to visit from V9. So you trace back to V7. You trace back to the last entry. So from if you have nothing to visit from V9, you trace back to V7. Then if there's nothing to visit from V7 because there's only V9 to visit from V7, nothing else to visit, so you trace back to V6. and then you have nothing else to visit from V6, you trace back to, and everything that has nothing to else to trace, just put across there so that you know that this is done. So V6 is done, then you go back to V3. V3 is also done. Yes.
V2.
Then you go back to V2. Then from V2, now you know that you've covered this thing. So you go to V5 next. And then from V5, you go to V8.
V8.
And then you see there's nothing to explore from V8. So V8 is done. Nothing to explore from V5. V5 is done. Nothing to explore from V2. V2 is done. And then back to V1. V1 is also. Is this fine now?
V1 to V4, I think.
V4, isn't it already covered? All right, then you write a V9, V4 after V8. Is this okay? And then
Ma'am,
when you make it, yes,
I have a small doubt. Directed or undirected, both are cyclic or not?
I suggest you to go through the definitions of what's a cyclic graph and acyclic graph and directed and undirected. These are very basic terms. We can't be discussing that here because we have only half hour left and we're left with the complete week 11 to discuss. These are just definitions, nothing else. Nothing that you need to understand. And
Ma'am, but you tell directed or undirected graph are cyclic or not, ma'am?
that's directed and undirected graphs can be cyclic and uncyclic, acyclic. There is
Okay,
no
ma'am.
particular rule for it. That's why I was suggesting you to just go through the definitions first.
Okay.
Okay, and if we'll make the DFS tree here, so we'll start with V1 and then we go to V2. From V2 we go to V3. Then to V6. And then from V6 we don't go anywhere from there. And then V3 we have V7. And then we go back to here, V2. And we have a V5 here and a V8 here.
V7 to V9 is possible, right?
Yeah, that's also here. So that's your DFS tree. So I think we're done with, okay, so there's one small thing that's left here, which is your tree edges and non-tree edges. So tree edges are these edges. So if you look at this graph, so this was your original graph, right? So every edge that you see here is a tree edge. So in this graph, because V1 to V2, you see here in this DFS tree, so this is a tree edge. This is a tree edge, this one. I'll just highlight the tree edges. Then this is a tree edge. But V2 to V4, because you don't see it in the tree, so this is not a tree edge. This is the tree edge. This is also a tree edge. This is a tree edge. A tree edge. This is a tree edge again. This is not a tree edge. And then this is a tree edge. So the left ones, this is left and this is also left. These are non-tree edges. Non-tree edges are classified into three. So one's called a forward edge, then a back edge, and then a cross edge. So a forward edge is basically where you go. For that, we'll need to discuss the counters. Okay, let's just quickly go through the what counters are and how do we keep them. So when you start from here, you put a counter here, the starting counter, the initial counter, initializing counter, which is, let's just say you put a 0 here. So this is 0. You start with a 0 only. You started with V1, so this is 0, and then you go to V2. So here you put the starting, when you started here. When you started exploring V1, you put a 0 here. And then when you're done exploring V1, you put the closing counter here on this other side. So V2 comes next, so this will be 1. And then after V2, you go to V3, right? So if you'll put here, you'll have a 0. Let's just do it in the tree itself. 0. Then you'll have a 1 here. Then you'll have 2 here. 3 here. And then you're done exploring this, so you have a 4 here. And then from V3, you go to V7. When you're done exploring something, that means that there are no other vertices left to explore or to visit from there. Then is when you put the end counter here, because there's nothing left to visit from V6, so we close it here on 4. And then you go back to V3. So from V3, you can go to V7, so you'll do a 5 here instead of here. You don't close it because you still have things to visit from here. So we have a 5 here, then a 6 here, then this closes at 7, closes at 8, this one closes at 9. And then you go back to here, but you don't close it because you have this to export. So you start this one at 10, then you go at 11 here, 12, 13, and then you close this one at 14. You go back to this one, start this at 15 because this is not yet explored. We still have vertices to visit from here. So this is 15, and then you end this one 16 and 17. Is this clear how you number the starting and the ending? We don't have a lot of time left, so just quickly a yes or no would be enough if this is clear or not.
Yes, ma'am.
Okay. And then if you see, so if you see something, we know that this edge, we discussed that from V9 to V6. So from V9 is here and V6 is here. So this thing that you have, this is not a tree edge. So from V9 to V6, it's not a tree edge, it's a non-tree edge, and non-tree edges are categorized into the forward edges, back edges, and then cross edges. So forward edge is basically where, as in this one, you have 6, 7, but 6, 7 is not contained in 3, 4. So this is a back edge, right? So all in all, if your 6, 7 interval is contained in, if this starting, if you're going from V9 to V6, so here you're going from V9 to V6, this edge goes from V9 to V6. So about this edge, your V9 is from 6 to 7, and your V6 is from 3 to 4. So if this thing 3 to 4 is contained in 6, 7, which it is, you say it's a forward edge. So this is a forward edge. And if you see the opposite of it, let's just say, if instead of this, you had this thing, if the numbering in this tree was in this, or let's just say, like, instead of changing this thing, let's just say if you change the direction of the edge, instead of taking it from V9 to V6, you take it from V6 to V9. If you have this thing, then V6 is 3 to 4, and this is 6 to 7. So in this case, this thing is contained. So from where you start is contained in from where you end to where you end, right? So this is going to be a back edge. If this was an edge, this would be a back edge. Is this all right? And if in case you see that these two intervals are disjoint, let's just say you have an interval 3, 4. Okay, wait. They are disjoint,
They are
right?
disjoint, ma'am.
Yeah, sorry. Sorry for the confusion. They are already disjoint. So this one is going. So all I'm trying to say is if you're going from VI to VJ and you see the starting vertex, let's just say this is AB and this one is CD. And if you see that your CD is contained in AB, then this is a forward edge. And if this is contained in this, if AB is contained in CD instead, then it's a back edge. And when you see that these two intervals are disjoint, then it's a cross edge, as in this case. 3, 4, and 6, 7 are disjoint, so this is a cross edge. This one's a cross edge. Even if you reverse the order, it will still be a cross edge. Is this part fine?
Yes, ma'am.
So these are how you identify the edges. And then next up we have week 11. So I'll start with the important algorithms only. First I'm starting with the easier ones for finding the minimum cost spanning tree. So I'm starting with those first. The minimum cost spanning tree is basically, let's just say that you have a graph in this way. And then you have weights here. So I hope everyone's familiar with weighted graphs. I'm not discussing the very basic terms here. I'll just write the terms here that I'm assuming you're familiar with. And if you're not familiar with the terms, you can just tell me. Let's just say that this is a weighted graph. 1, 2, 3, 1, 4. Okay, I think the graph's not clear. Let's just say you have this thing, and this is 1, 2, 3, 4, 5. Let's say these are the weights on the edges. So there are two. So what are we intending? So in a minimum cost spanning tree, what you want to do is you just need to find out the edges here, the edges that you need here. So you just need to find a tree from this one. I know that this is okay. This isn't a tree because it already has a cycle here. So I just need to find a tree here such that the cost is minimum, right? So cost is minimum, as in what you can do is you can just remove this edge and then it will be a tree, right? If I'll remove this edge, this one, this edge, if I'll remove, then it's a tree. But is the cost minimum? If I'll remove this thing, will the cost be minimum? Because let's just say if you remove this edge, you'll have 1, 5, which is 6, then you have 8, and then 12. So you'll have the cost as 12. But if you remove this edge instead, you'll have 1, then 3, 6, and 10. So you'll have a lesser cost than this, right? And then maybe if I'll remove some other edge, I can have even lesser weight, lesser cost. So I need to make sure, I need to just find a tree which has minimum weight. So how do we have algorithms for it? So the first algorithm is, let's just have a 1 here. The first algorithm is your Prim's algorithm. So in Prim's algorithm, what you do is you just take the edge with the minimum weight. So with minimum weight, there are two. So this one edge has weight 1, and then this also has weight 1. So you can choose any one of them. Let's just choose this. This one has been chosen, and then you choose the ones that are connected to this vertex or this vertex. So none is connected to this one. V5 has no edges at all. So you just go to this one or this one, and then you choose the minimum one. This one, this one. Out of all the outgoing edges from V1 and V5, you choose the one with minimum weight. So this is the next minimum. This one is the next minimum. And then from here, V4, you don't have anything from V4, right? So next up, what you do is you choose this one because you're not left with any choice. V4 does not have an outgoing edge, so you can't choose from here. So you will choose this one. The next chosen one is this one. And then from V3, there's only one edge, which has it been chosen? So you choose this one next, the third one. And then from here, from V2, you choose the one with minimum. So this has 2 weight, this has 4 weight, so you choose this one. So the edges that you've chosen are these ones. V1 to V5, and then V3, V4, V2. And we won't choose this one actually. We started with the minimum thing, right? So we choose this first. Then next up we choose this one. Then because we can't choose anything else from here, so we choose this one next. And then from here we choose this one. Yeah, so we don't need this edge. So this has weight 1, this has weight 5, this has 3, and this has weight 1 again. And every vertex has been covered. So this is the minimum spanning.
Please explain again.
Yeah, we'll explain this.
Algorithm.
Let's just 1, 5, 3, and the weight of this is 1, right? So this is 8, 9, 10. So this is 10. What you do in Prim's algorithm is you start with this. Okay, you start with the edge that has minimum weight. So either this has minimum weight 1 and this has minimum weight 1. You can choose any one of them. Let's just say I'm choosing this one. You can choose anyone, but let's just say I'm starting with this one. So we need to find the minimum cost spanning tree, right? So we're trying to make the tree. So this is, you add V5 then. And then out of these, you see which ones, because V5 has nothing else connected to it. So you can't go from V5 to anywhere else. Otherwise, you would have started exploring, with the edges that are connected to V5. If this has something else here, you would start with the edges here. But since you don't have anything here, you go back to this thing, V1, and then you see which one has which out of the remaining two has the minimum weight. So you choose this one. This has weight 1, this also has weight 1. And then you go to V4, and unfortunately V4, some reason V4 does not have an outgoing edge. This does not have an outgoing edge. Otherwise, if let's just say this graph was, instead of this direction, if you had this direction, then you would have to choose this one. You would be left with no choice and you will have to choose this one. Is it fine? But because the direction is because you're directed this way, so you can't choose this edge. And then you come back to this one, V1. So you can only choose this edge. So then next up, you choose the 5 weighted edge till V3. And then from V3, there's only one edge. So you can only choose this edge. And you will have to choose this edge because every vertex is not yet covered. V2 is not yet covered. So you'll have to choose this thing and then you'll have a 3 here. So this is what you got here. And now if you see every vertex is covered, so you don't need to continue this thing. Is it fine?
Ma'am, I have sent a doubt. I have a question. Can you explain? I'm
Yes.
sending in the chat box. Okay. I'm sending.
So, ma'am, Prim's algorithm is the minimum cost spanning tree.
Yes, it's for minimum cost spanning tree. Wait.
Okay.
Ma'am, please check your inbox, ma'am.
Okay, just give me 1 second.
Okay.
So you have
Position 1, this is 2. One.
No.
Is there a problem? This is the tree, right, that you've sent me.
Wow, thank you so much. Yes, ma'am.
Okay, so we'll start. If we use the Prim's algorithm here, so the minimum weight here is this one. So you start with CD first, and then because it's not directed, so you just look at the edges. So the minimum one here 9, 5, 3, and then here 2, 9, 8. So the minimum is 2 here, right? So you'll go to F 2, and then from here 7, 8, 9, and here you have 3, 5, 9, right? You have these things 7, 8, 9, and then these things. So out of the minimum here, you get a 3 here. And then
DD,
what else is left?
Ma'am,
DE.
You can go to this one.
Ma'am, DE. DE is the next
madam.
list.
Ma'am, I solved this
Yeah, I
question
just
by
want to
A
make
to
sure that
B, B to F, F to C, C to D, D to Z, like this. Then I am getting the answer 24, but in the correct answer is 23.
Yeah, ma'am. Now you can draw A to B4.
It's in the virtual algorithm.
Ma'am, A to
A to
B.
B, B to and B to
just
F.
1 second. Everyone else can unmute themselves.
From
We
node
can't
A
cover
to
this
node
edge
B.
because we've not reached A, so we can't use this one. That's not how Prim's algorithm works. You can't choose
Ma'am,
A, B yet.
Why?
ma'am, you can. That's how I got
Prim's algorithm,
23.
you can, yeah, that's the Kruskal's algorithm. You can't use that here. In Prim's algorithm, you do it differently from Kruskal's algorithm. You don't
Okay, then,
directly
ma'am.
choose the minimum weights from here.
Okay, then from
Okay, then
D
you
to
can unmute
E5.
yourself. The next one, the next minimum is, I guess, this only,
Yes.
because we've covered everything else. And then from
Then
E, it's 7. So the minimum ones that we have to choose from is these. We can't choose 4 yet because 4s we have not covered A yet. And
Ma'am,
then
BF we can choose BF now.
yes.
yeah, you
After
can choose
BF,
BF, but
then BA.
we have things smaller than 8 here. We have 6 here, so we should choose this first.
But
But
ma'am, this will
that'll
But
be
D
a
has
cycle,
already been
okay.
chosen.
That'll be a cycle. You can't
Ma'am,
choose.
BF. After that, BF and BA. Then it comes
Okay,
as
you can
23.
unmute yourself. Because if everyone keeps talking, then it's difficult to finish everything in 11 minutes. This is these two edges and 7, 8, 9. So we have nothing lesser than 7 here. So let's just choose this one. But then it'll close this thing. So you can either choose. I just want to make sure that there's
Ma'am,
no edge with
CA, ma'am.
lesser weight. CA. Yeah, you can either choose CA or you can choose this thing. You can also choose this edge. So either you can choose this one or you can choose this one. Let's just choose CA. So we'll have an 8 here. And then you can choose B with the minimum one. So we'll have a 4 here. And I think everything is covered, right?
Yeah, now it's 23.
So it's 8, 4, 12, 13, 14, 15, 20, and 23. This turns out to be 23. You could have chosen this also. You can remove, but it'll be the same thing. Then you'll have to remove this. That works too. And then for the next one is the Prim's algorithm is clear to everyone, right?
Ma'am,
Yes.
I'm not getting, ma'am. Can you explain again, please?
Okay, you start from the minimum edge, the minimum weighted edge. So you start from here because you only have one here. So you start with this edge, CD, and then you look at from D and from C. So you have these edges here. This one, this one, this one, and this one, this one, this one. So you choose the minimum out of these. So the minimum is this one. So you draw this edge then. And then you see the minimum out of. So you have now covered F. So you can have a look at these two as well. So you now pick a minimum out of all of these edges, right? So the minimum is now 3. So you add this edge next. And then you add, so G is also there, but now this is there, you could have chosen this too, but this will make a cycle. So we are avoiding this one. And then out of the left ones, because this is already done, this is done, this is done, this is also done, this is also done. So you're only left with these things, right? So you have to choose out of these only. But if you choose 7, then there'll be a cycle. So you can't choose this one. If you choose 8, so 8 is actually lesser than 9. So you should choose a edge with weight 8. So either you will choose this edge or you will choose this edge. So I've chosen this one. The answer is not going to change. The minimum cost is going to remain the same, no matter which edge you choose out of these two. So if I choose 8 here, this is 8 and then this gets unlocked. So you can choose this next 4. And now because every edge is covered, so you don't need to continue this thing. And you will get your
Okay,
minimum
ma'am.
weight as
Got it.
23.
Thank you, ma'am.
Then you have, no problem. Then you have Kruskal's algorithm. And make sure that you follow the orders, because sometimes you can't choose this edge directly. Even though you can see that this is the minimum weight out of whatever's left. So out of these circle ones, this is the minimum one. But you can't unlock it yet because you have not reached B or A yet. That's why you can't use this edge until you've reached B or A. So you can only choose this edge after choosing this one or this one or this one.
One more question.
Sorry.
In the I already sent in chat box, please.
Sorry, what?
I have a doubt in one more question. I already
Yes.
sent in chat box. Please check.
Can we do the question later? I can't anyway see the question.
Okay, ma'am. Okay, okay. No problem.
Yeah, I see the question now, but let's just do this later because
Okay, ma'am. No problem.
okay.
After
So
revision class is all out. I have so many questions that I will clear after revision.
okay. So for Kruskal's algorithm, what you do is, so let's just draw the same tree here, this one only. So if you do it by Kruskal's method, what you will get is, let me just draw the tree first. So in Kruskal's algorithm, what you do is you arrange these edges in ascending order of their weights. So the first one will be this. So the least weight is this. So you choose this one, CD first, because this has the least weight. But then you choose the one with the next minimum weight. So the next minimum weight is 2. After 1, you have 2 here. Because we don't have any other one here, so we'll choose this. And then just 1 second. Yes, so when you do it as per the Kruskal's method, so there's only one here. So only one edge has weight 1. If you had any other edge with weight 1, then you will include next that one. This one has the minimum weight, and then next up you have this weight, and then next up you have this 3. So you keep arranging them in ascending order, but just make sure that there's no cycle. So you have 3 next, and then you have 4 here. So you take A to B, 4. And then you can't take this. Okay. Then you take the 5th one here, E, 5. But you can't take the 6th one because then it will be a cycle. So you avoid the 6th one. Then you take the 7th one. 7 is this. So you can't take this one because then again, if you take this one, you will have a cycle here. So to avoid a cycle, we don't take this edge. Then next up we have 8. So we can take this 8. And then next up we have 8 here as well, but we don't need this because then it will be a cycle. And yes, we have covered all the vertices, right? So we don't need any other edges. And if you see the total weight here, we'll have 4, 8, 2, 5, 1, 3. This is 12, 13, 14, 15, 20, and this is again 23. So no matter which approach you follow, the tree, okay, in this case, you're getting the trees also the same. So the trees that you get are also the same in this case, which is not always true. So what happens is when you have all the weights different, no, this is just a coincidence. So this generally happens when you have all the weights different. When you have all the weights different, then your minimum cost spanning tree, as per both Kruskal's algorithm and Prim's algorithm, is the same. But it can be different. So the minimum cost spanning tree doesn't have to be the same from both the methods, but your minimum cost is going to be the same from both methods. And with this, we're done with the Kruskal and Prim's algorithm, and then we'll start with
Ma'am,
Dijkstra's algorithm. Yes.
ma'am, I have shared one diagram in message chat box.
Is it based on minimum cost spanning tree?
Yes, ma'am.
We can't possibly do all the questions here because we have to do two major algorithm, Dijkstra's algorithm and Bellman-Ford algorithm. We'll just take up this one. So what does the question say? Does it have to be done using the Prim's algorithm or the Kruskal's algorithm?
It's just asking for minimum cost spanning tree of the graph given below. What is the weight
Minimum
of
cost or minimum cost spanning tree? Because minimum cost spanning
sorry,
tree can be
minimum
different.
cost spanning tree.
Okay. Just 1 second. So you again start with what happens here is this is what I was talking about. So if you see all of the weights are distinct, right? Except for this last one that you have. So in this case, you'll get the tree using minimum cost. The minimum cost that you get is same using both the methods. So no matter what method you use, it will be same. But the tree can differ as per what you're using. So if you're using Prim's algorithm, you can get something different. But in case you have all the weights distinct, then you will get the same tree from both the algorithms. I hope that part's not something very important, but I was just telling you so that you just know how it works. So you start with the minimum weight here, which is 1. So you add this
AB.
edge,
Yes.
and we're using Kruskal's here. Let's just use Kruskal's method here. Then you'll get a 2 here. And then 3 will make a cycle, so we're skipping that. And then we'll have a 4 here. Next up, we'll have 5 here. 6 we're skipping because that will be a cycle. Then we take 7. 8 we are skipping because that will be a cycle. Then we take this G, 9. And then no matter these two edges are same, so no matter which one you take, this one or this one, I'm taking this one. So this is a minimum cost spanning tree, or you can remove this one and have this edge. That's also a minimum cost spanning tree. And if you add all of these, you'll get the minimum cost. This is one. Is this fine?
Yes, ma'am. It's fine, ma'am. Thank you. Actually, I was getting 40, so that's why, ma'am.
Now it's fine, right?
Yes, ma'am. Now it's
Must have
fine.
made a minor
I
calculation
have
mistake.
taken it from D to instead of taking B to E, I have taken C, D, D2 and E. So that's why.
So you use Prim's algorithm.
Yes, ma'am.
That should be the cost shouldn't change. Do you want me to try using Prim's? Or is it fine?
If you wanted to show us, ma'am, you can.
Okay, using Prim's, you'll have. Let me just remove this entire thing from them. So using Prim's, you'll have. You start with this edge only, but then you have these two connected to these two, right? So you take the minimum 1, 2.
1, 2.
And then you have this unlocked, and this one's also unlocked, right? So out of these, you take the minimum one. So you can't take 3, you'll take 4 then. And then this gets unlocked, this gets unlocked. So out of these, you choose the minimum.
D to E.
So you will get this. You'll get this one, right? You'll have to choose the minimum out of this.
Oh, okay, okay, yes.
That's how Prims work. So you'll have a 5 here, E. And then this gets unlocked too. So you'll choose the minimum out of these 3. So it's this one. But you can't choose this because it will form a cycle. So you'll have this. And then this gets unlocked, this gets unlocked. So out of these, you choose the minimum. So you can't choose this one because it works the same way as, I think we'll get the same tree. As I said, we'll
Yes,
get the
ma'am.
same
Yes, ma'am.
tree as that.
Yes, ma'am. Getting same answer. Okay, got it,
Thing
ma'am.
using
Thank you.
both methods.
Yes.
Okay. So let's move to the Dijkstra method then. The Dijkstra method is basically for finding the minimum distance from a given vertex to all other vertices that are in the graph. So let's just do it using a problem. We'll do it with the help of a problem. Let's just say you have this thing. Okay, let's just do this one only, the graph that we already have. Let's just do the extra for that only.
Ma'am, any trick
Don't have
for
negative
understanding
weights here.
the alls algorithm? Any short trick
Or trick for what?
for understanding the all false algorithm? Like
Short
Prim's
trick, they're already
algorithm?
short only. In Kruskal's algorithm, you just arrange the vertices. So you just arrange the edges in this manner. If you have this graph, you arrange AB first because it has the arrange them in ascending order of their weights. So this has the least order, least weight. You write AB, and then AC is next, and then you just keep adding the edges. What's there? No shortcut is needed because this method itself is very short. The method itself is a shortcut. There's no shortcut to it. Okay. So we were doing the Dijkstra. Let's just do the Dijkstra algorithm on this only. So let's just say we need to find the minimum distance of every edge, every vertex from this vertex. So this, let's just call this the source vertex. A is the source vertex. So A will be at 0 and then everyone else will be at infinity. And then from here you'll have, this is 0, this one is fixed, right? Minimum distance of A from A itself is 0. So this is fixed, and then you have 0 here, 1 here, 2 here, and everything else is at infinity because these vertices do not have an edge, a direct edge with A. So we have infinity here. And then we take the minimum of these, the directly connected ones to A. We take the minimum of these two, which is 1. And then we fix it. So B is now, the weight for B is fixed. So you have 0 fixed, 1 fixed, and then from 1 you go to the other vertex. So this is 1 plus 5. So to E you'll have 6.
Ma'am, first row should be A, right? Sorry, first column.
This one?
Then it should be C to B should be 2.
I don't understand what you're asking.
We are seeing the column and rows, right?
So we just write the distances here, and we just take the immediate vertices to this one. So the immediate vertices are B and C, and then we, instead of writing these at distance infinity, we write the distance here as 1 and 2 because they are next to A. They're directly connected to A.
Here the distance is infinity, let's assuming, and after this what is
Okay,
the distance
no,
between
I
A
got
to
it.
B, then just writing in descending order, right, ma'am?
I don't think I didn't.
Ma'am,
Yes.
I told just in infinity, here is a descending infinity, just assuming, and after this I'm going in the descending order, like
Yeah, descending
from
as in not descending order. You pick out of these two, you choose the one with the minimum weight. So because this has the minimum weight, you
if
pick
this
this.
is connected to another vertex, then we are writing, otherwise not, right? Yeah, also I
Let me
can
just, I
write
don't
in
think I
the
understand the question. I'll just repeat the algorithm till now. What you do is you start with this one. So A, this is, initially you take A to be at 0, which is the source. You take the source to be at 0 and everything else to be at infinity. And then you see that A is directly connected to B and C. So you update these distances. You update the distance to B as 1 and to C as 2. Because this distance is 1, this is 2. You can't update these because they are not directly connected to A. And then you choose the minimum out of these two. So the minimum is 1. So you fix this one. What you do is you want to find the minimum distance of each vertex from A, the source vertex. So the distance here is fixed now. The minimum distance of B from A is 1. This one is fixed. When I say that this is fixed, I mean that the distance of vertex B from A is fixed as 1. They fix this. Now you don't need to change this thing. You can't change this thing in further iterations. And then you start with B because this has out of these two, this has the minimum one. So you write a B here. You don't actually need to write it, but we just write it to make sure that B has been, the minimum distance to B has been discovered. You don't even need to make this block. I'm doing all this to make sure that I know that the minimum distance to B has been found to be 1. That's all. That's why I'm marking all these things. You don't have to do that. So the distance, so after, then you start visiting the direct neighbors of B. So B has directly an edge with C. So so the distance to C will be 1 plus 3. So the previous distance, the distance till 1. 1 is being fixed here. The distance 1 and then plus 3. So you'll have a 4 here. But see, you already have 2 here. So you don't need to update it. You can keep it as 2. So this will remain 2 because 2 is lesser than 4. Instead of doing this, you can just directly go there. So we'll have a 2 here. And then the next vertex that is directly connected to B is E. So B has fixed shortest distance 1. 1 plus 5 will be 6. So you'll have a 6 here. And everything else is at distance infinity from B. So you keep it as infinity. And then you see the minimum distance from here. So this minimum distance is already fixed. You don't consider this. You consider the remaining one. So the minimum distance here is if this gets fixed. That means the distance at C is fixed. Now you fix the distance at C as 2. So the minimum distance, the shortest distance of C from A is 2. 2 is fixed, 1 is fixed. Now we're calculating for the other ones, other vertices. Now from C, you start visiting the neighbors of C. So you have 4 here. There's only one B. So you have 2 already here, and 2 plus 4 is going to be 6. So D is going to be 6. This is already 6. This is 2, 1, 0. And everything else is at infinity. And out of these, so this is already done. So out of these, the minimum is, you can choose whatever you want because these two are same. So let me just choose D first. Let me just fix D. So that this distance here is fixed now, 6. So this is 6. And then if you will just check this one, you'll have 6 plus 6, 12. But E already has 6. 6 is lesser than 12, so you don't update it. Then from D, you go to F. And D plus, so this is 6, and 6 plus 8 is going to be 14. And 14 is less than infinity, so you update this thing. So you update this 14, 6, 6, 2, 1, 0. And because this is already fixed, so you're only left with these. This is still infinity. You don't have a direct edge with G. You don't have a direct edge with H from D. So these two are still at infinity. Now you choose a minimum from these two. The minimum is for E, right? So you write an E here. And you block this. That means now you can't change this thing. So the minimum distance of E from A, E is here. This is going to be 6. So this is also fixed, right? This is fixed. This is fixed distance. This is fixed distance. This is fixed. This distance is fixed at 0. So do I need to complete this or is it fine? Now you know how it's to be done, right? You just choose the minimum and then you just add the distances, upcoming distances. It's almost done, by the way. So from E, you'll have, at E you have 6 and then here you have 7. So 6 and 7 is going to be 14, which is already 14 here. So you don't have to update it. These two are fixed, so you don't change all of these. And then you don't have a direct edge here, so you just have infinity. And now you explore F next, because this is the only one left. Nothing else is left. Everything is marked, right? E is, you have found the minimum distance till E, so you can't choose these things. Then you choose this. And then from F you will have, so at F you have distance 14. So the minimum distance till F is now fixed to be 14. You can't change this 14. This is fixed. And then 14 plus 9 is it's 23. And then 14 plus 7, 11 is 35. Right? So you will have a 35 here and a 23 here. So out of these, the minimum is this 23. So next up, you fix the distance at this 23. And then you see 23 plus 11 is how much? It's 33, 30. And here you have 35. Get a 35. That's fine. Now you have a distance for each vertex. Minimum distance for each vertex from source A. Is this fine?
Yes, ma'am.
Okay. This is the Dijkstra's algorithm for finding the shortest distance from a source vertex to every other vertex.
So here it is 14, right, ma'am?
Yep, it's 14 here. At F, it's 14. I just wanted these ones to be distinguished from these ones. So I just encircled it darker. This is 0, 1, 2, 6, 6, 14, 34, and 23.
So this
Next up,
approach is
you
called
have,
greedy approach, right, ma'am?
Yeah, it's called greedy because you're not actually, what you're doing is you're not exploring every part of it. You're just directly jumping to points. That's why it's called greedy approach. And then you have Bellman-Ford approach. So Bellman-Ford is, and this only works when your weights are positive. All weights are greater than equal to zero is when this approach works, and it fails when you have negative weights. Bellman-Ford is, you can use it for positive weights as well, but it's only advised when you have negative weights. If you have positive weights, this is a better method to use. In Bellman-Ford algorithm, what we do is we'll have
Ma'am,
yes.
ma'am, can we use Dijkstra's method when we have a cycle which has net weight not negative but it is zero? The weight of
You
the
have
cycle is zero.
see, the only condition for Dijkstra's method is you need to have all the weights as positive. That's the condition. So if you have all the weights positive, you can't get a cycle with zero weights, right?
Okay. Oh,
You
okay.
you
Thank you.
can't use the extra method here. So this is and for negative weights you can use Bellman-Ford, but make sure that you, and if you, we've already discussed this in the summary part, that if you have a cycle with negative weight, you can't use Bellman-Ford, you can't use the extra method, so you don't have any methods if there are negative cycles. And Bellman-Ford helps you to identify negative cycles. Okay, so how does Bellman-Ford work? Let's just have a graph first. Let's just say you have this thing and you're starting with, this is your source point. What you do is, so the maximum number of iterations that you actually need to perform is the number of edges minus 1. The number of edges are 1, 2, 3, 4, 5, 6, 7, 8, 9. So after 8 iterations, you should get your answer. And if even after 8 iterations, you still keep getting better answers, that means you have a negative cycle. That's how you identify that your graph has a negative cycle. Is this part clear? We'll discuss the algorithm, but I just want you to know how you identify the negative cycle. But that's not, you won't be asked questions on that by the way. Okay, so starting with this thing, you have, let's just mark these vertices A, B, C, D. We start from here, the distance is 0 here, and all the others are at infinity, right? You start just as in Dijkstra, but then later things change here. So you have B and F directly connected to it. So this is 0, and this is 4, and this is 6. Don't take the minimum of these. What you do is, explore both of these, and so if you'll go by this way, you'll get 4, and minus 2 if you'll get 2 at F. So at
2.
F you'll get a 2,
Yes.
right?
Yes, ma'am.
And then if you'll go at E, you'll get 4 plus 2, 6, right? You'll get, at E you'll get a 6. And at C you'll get a 4 minus 1, 3, right? So you'll get a 3 here, and the others are not directly connected, so you don't need to do that. And then from F, if you do it, so F you need to do it in this iteration only, 0 and 4. So even if you do it, okay. and then you do from this f part. So 6 and then 6 minus 2 is 4, right? But you already have a 4 at B, so you don't have to change it. 6 minus 2, there's already a 4 here, you don't change it. And then 6 minus 1. So at E, you should have 5, but you have something better here. You have 6, sorry. You can have 5 here instead, right? E is still at infinity. So you have 5 here at E because you get a better weight from here. 6 minus 1, 5. And then nothing else is directly connected to F, so you close it at it. So these are the final things that you get after this iteration. And then in the next one, what you do is, now you've reached to E and you've reached to C, right? So from here you continue. So at C you have distance 3. And if you go from C, so you visit every vertex that can be visited from C. So C has 3. So 3 plus 3 is going to be 6. But E already has 5, so you don't need to update it, right? Then at C you have 3. If you go here, you'll have 4 at D, right? So at D you can update it, update infinity as 4. 5 you can't update. 2 is not directly connected to C, so no need to update yet. And then 3 here, 4, 0 is not to be updated, right? This, and then you go to E, because E is also on level 3rd. So you go to E, and then from E you'll have, at E you have 5. But if you don't have a direction here, then you can have 5 minus 1. At F you can have 4, but you already have something lesser, which is 2. So you will not update it to 4, you will keep the 2 here. And then here you have, at E you have 5. 5 plus 2 is going to be 7. So you won't update D either, you keep it as 4. And then from E you can go to C. So E has distance 5 and this is 3. So this is going to be 8, but at C you already have 3. You have a better distance here, so you don't update it. And then in the next one you have D, right? So you start from D. At D you have distance 4. So if you will go to this one, you will have 4 plus 1, 5, but you have a better distance at C, 3. So you don't need to update this. And this is 4 here, right? In the last iteration, D has 4. So 4 minus 1 is going to be 3. So you can update this one, 3. And then you are at E again, because you've only changed E. So from E you have a 3 here and a minus 1 here. What the problem here is, now there'll be a problem here, because this will, if you do it this way, this is never going to end. So we should probably have directions there, because this is an undirected cycle. Can you see the problem here, that your D and E will lead to the reduction of the weights for each other? So if you have a 3 here, then for D you'll have a 3 minus 1, 2. So you'll have a 2 at D. And then for D you'll have a 2 minus 1. So these both will keep reducing the weights of each other. That's why you need to have a direction here. So let's just keep a direction here so that we know where we're going. Let's just say this is the direction. Now, in which part have we done it correctly as per the directions? I think we've made a mistake on the last step only, as per the directions. So if you have directions now, which edge were we on? This was level 1, level 2. This is 1, 2. So you must be here then. And then from C, you can update this 4. So this remains same 4. From C, you can update E. At C, you have 3. And then here you have 3 again. So it will be 6. So you should not update E. You have a 5 here already. So you should keep 5. And then F is not directly connected. So you can just keep 2 here. And then D we have already done. The others are not directly connected. So we can keep them as they are. And then from E, because E is also on that same level. So from E, you can't go backwards. So you can just go here to D. So E is 5. 5 minus 1 will be 4. And D is already 4. So you don't need to change. So I think this will be the final thing. Even if you will perform one more iteration, you'll get everything same. Is this all right?
Yes, ma'am.
If there's anything that you don't understand, you can ask. Because even if you'll perform any, you'll end this thing here because you've reached D. And now there are no outgoing edges from D. D was on the last step and you don't have anything else, any outgoing edges from D. So you end this thing here. This has ended now. These are going to be the minimum distances, shortest distance. These are the shortest distances from source 8 of every other vertex. Is this fine?
Ma'am, so Bellman-Ford algorithm is not applicable for undirected graphs.
If you have an undirected graph, no, as we discussed this thing here, it might be, we can't really say for sure. But what was happening here is if you have an edge from here to here, and then if you have an edge from here to here, what happens is, let's just see this thing. The main problem is, I'll just write it. You can do it in that case as well, but the problem here is that this is almost a cycle. So cycle in the sense it's not actually a cycle by the definition of cycle. E to D is not a cycle, right? But you have -1 here and then you have -1 here. So this is a negative thing. It's actually creating a negative loop here, which is minus. So what happens here is each time you go through this loop, let's just say if you had this edge and if you also had this edge, you go from here to here, you'll update D to be the. So this will get updated as, let's just say we have a 4 here, this will get updated as 4 minus 1. So you'll have a 3 here. Then you'll update this thing as 3 minus 1. And this will get updated as, so let's just say you have 5 here and 4 here. So if you start from here, you have 5 minus 1, 4. And then if you go backwards, you'll have 4 minus 1, 3 again. And then you'll have a 2 here, a 1 here, a 0 here, -1. So you'll keep getting lesser weights. So there's no finite end to it. That's why you can't. So in a way, you have a negative cycle here. Is that all right? So when you
Yes,
have a
ma'am.
negative cycle, you can't use any algorithm for that. You won't get an answer. It's not about Bellman. You can't use any other algorithm. At least not the ones that are inverse limits. Then
Okay,
you
ma'am.
don't get a finite answer. This helps you detect cycles if after a certain stage. So we say that the maximum number of iterations, this we were able to do in 3 iterations, right? We only did 3 iterations. But if it takes more than 8 iterations, because there are 9 edges here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 1 is 8. If after 8 iterations, you still keep getting lesser numbers here, lesser weights here, that means you have a negative cycle. That's why you keep getting negative. Lesser weights, and then lesser weights. There's no end to it. So that's how it helps you detect the negative cycles. Is it fine? Okay.
Yes, ma'am.
And the last thing that we have in this syllabus for week 10 is week 11 is Floyd-Warshall's method. So, or Warshall's method, it's in this method, what you do is, let's just say you have, let's just take an example, start with an example only. Just name them A, B, C instead then. Let's just say you have this thing. So what you do is first you make a matrix of these, the adjacency matrix for this. So the adjacency matrix is going to be, I'm not writing these things. already have this matrix, you can check with it. Let's just say, so this is the adjacency matrix for this graph. Then next up, you make this thing. You shouldn't be doing this. Let's just call this matrix M. And let's just call this one MA. So MA basically means, so you got the same ABCD thing here. And then in this matrix, what you do is,
Ma'am,
so instead of yes,
from A to A, you wrote there's 0. There also we're supposed to write infinity, right?
no, this is adjacency matrix. From A to A, it's 0 only.
Okay.
From the vertex to the vertex itself, you always have a 0. That's why the diagonal is always 0 for an adjacency matrix. And then here you keep the diagonal same. So what does this matrix represent? This basically represents the, so in this matrix, what you do is you choose any one vertex. So you've chosen A here, right? You've chosen vertex A. And then you see that from A to A, so that's why I'm saying that you keep this. So you've chosen A, so you keep this A1 and A. So the A column and A row you keep same. So you keep 0, 3, infinity, infinity. 0, 2, infinity. Keep this and this. The A column and A row you keep the same. And the diagonal one you also keep the same. What do you change in this MA? This is basically, if you will go from, so AB, this is A to B, right? So this is like, if you will go from A to B, we don't need this one because it's already fixed. Let's just say B to C. So if you have B to C, this basically means the BCth entry. So this MA's BCth entry. BCth entry is going to be minimum of M's BCth entry and M's B to 1 and B to A entry and M's A to C entry. So what does this mean? This basically means, so this is, I'm not writing capital B because, okay, let me just write capital C. What does this thing mean? This is the matrix MA, right? This is the matrix, and this is the BCth entry. BCth entry. So the BCth entry is basically, either you take the BCth entry from there, BCth entry of this initial matrix, or you take B to A from this matrix and then sum with A to C. So B to A here is 3, right? And then A to C. A to C is infinity. So 3 plus infinity is infinity. So in this case, you'll get an infinity here. And from B to C, you get a 2. So minimum of 2 and infinity is 2. So you get this term as 2. So this term here, BCth term will be 2. Similarly, you do this for all the other terms. Is this all right? Is this part clear?
Can you explain this again? This point.
Okay, let's just do one thing, right? I think the ABC thing is a little confusing. Let me just write 1, 1, 2 instead, because that, instead of A, B, C, D vertices, let me just call them 1, 2, 3, 4 vertices. This is easier. And then in this, you'll have, let's just call this thing as M1. 1 I've just written because for this entry, so for the, this is the matrix notation for this matrix, right? And how do you define this matrix M1 and the 1, 2 entry, not 1. So as I said, you keep the diagonal entries same. Keep the diagonal entries same. Keep the first row and first column same. So while making this thing, you keep this first row because 1 is here. So you keep the first row and first column. You keep that same. And you keep the diagonal thing same. And then what do you change? You change these entries, the other ones. So you'll change 2 to, let's just say you want to find 2 to 4. This time you want to find 2 to 4. So how do you do 2 to 4? So you take from the previous matrix, this one. You see 2 to 4 entry. And you see M2 to 1 plus M1 to 4. That means you insert a 1 here. You have 1 here, so you insert 1 in between these two, and then you find the distance from 2 to 1 and 1 to 4. So what you're doing is 1, 2, 3, 4. If you have this thing here, so first one was the direct distances. This connection is basically the direct distances from this to this to this, right? And this one is what? So it says this one means you have to go via 1. So this will mean that if you're starting from 3, let's just say you want to go to 3 to 2. So you'll have to go via 1. But if you can't go, because 3 and 1 do not have a direct edge. So 3 and 1's distance is infinity, right? And then this distance is 2. So you just directly take an edge from 3 to 2. In this case, you don't have a direct edge from 3 to 2, so it will remain infinity. So 3 to 2 is going to remain infinity. Is this a little clear now?
Man, 2 to 4 will be 6, right?
If you have to do 2 to 4, let's say 2 is here and 4 is here. So this, you have to go via this, right? So this is 3, 2 to 1. First you'll go and then you'll go 1 to 4. So this is 3 plus 3, 6. But we have to, either we take it from here or we take the one that is directly here. So 2 to 4, if you'll directly go from 2 to 4, it's infinity, right? Because you can't go from 2 to 4. So directly from 2 to 4, this one is infinity. And from here to here, 2 to 1 is going to be 3. 1 to 4 is going to be 3. So this overall is going to be 6. This is 6 and this is infinity. And the minimum of these two is going to be 6. So your 2/4 entry is going to be 6. Similarly, you can do it for these 3 entries as well. Is this fine?
Yes, ma'am.
Should I do these 3 entries as well? Do in M2 matrix. So in 1 to, and then you add these two distances. And these distances you take from this matrix, right? So if you want the entry from 2 to 3, you go from 2 to 1. In this matrix, you go from 2 to 1. And then 1 to 3. So you take the distance 2 to 1 from here, add the distance 1 to 3 to it, right? 2 to 1 plus 1 to 3 distance you add. And then you see the direct distance 2 to 3. So whichever is lesser, the distance 2 to 3 or 2 to 1 plus 1 to 3. So whichever is lesser, you take the minimum of it here. The similar thing you do with M2. So in M2, what you do is, let's just say you want to, so the second one, because it's 2 this time, so you keep the second row and second column the same as the previous one. So this is your second row, you keep it as same, 3, 0, 2, 6. This remains same as this one. You keep the second column same, so this is 2, 0, infinity. And we don't know what here is. There was something here, we didn't calculate it. We need to calculate all the entries here first, and then we move to M2. And the diagonals are also always 0, 0. So this diagonal has to be kept 0, 0 only. Second, because you have a 2 here, so the second row and second column have to be kept the same as the previous one. And then let's just say you want it from 1 to 3 this time. So you go, either you take the distance this 1 to 3 or 1 to 2 plus 2 to 3. So you're doing the same thing here, but with 2 this time. So if you want 1, 3, either you calculate 1, 3 directly from the above, the previous one. The previous one is this one, right? So 1, 2, 3 directly from that one. This is this entry. This is M1 of 1, 3, right? This entry. And then else you do 1 to 2 and then 2 to 3. So you insert a 2 between 1 and 3. And then you take the distance from 1 to 2 and then from 2 to 3. Then you add these two. And whichever is lesser, minimum of these two, you write here in 1 to 3 in this entry. Is this fine? We have to wrap up this class in 5-6 minutes. So is it fine? You understand
So,
what we're doing?
so when we proceed with each matrix, we proceed according to the previous one,
Yes.
the previous
So
matrix
this
which we got.
matrix, the previous one, this. Yeah. Then, so this is for the vertex 2, right? You're inserting vertex 2 in between the given vertices. So for 1, 3 entry, you insert 2 in between, right? So this is for 2 vertex, then similar one. And then you do for M4, the 4th vertex, and you use this matrix, the previous one. And this matrix, the last matrix, because you have 4 vertices here in the graph. So the last 4th matrix is going to give you the shortest distance of each one from each of the other vertex. Is that all right? And by the way, you don't need to follow this order. You don't have to do like, let's just take one first, then we'll take 2. You can take 1, or you can start with some other vertex. That's fine. You don't have to start with vertex 1, then 2, then 3, then 4. You can do 2 first, but for your own good, you should be starting with 1, 2, 3 because it's easier to remember. That we're doing it in ascending order. Is that all right?
Yes, ma'am.
Okay, so this was the last
Yes, ma'am.
topic from week 11, and everything is revised now. If you have any doubts, any things to ask, you can do it in like 5 minutes because, and we'll wrap up this session. Does anyone have any doubts in anything that we've discussed so far? Or from week 11, week 10? Okay, so I think there are no doubts because no one's responding. So we'll wrap up this session.
Ma'am, are we going
Okay.
to expect questions from this?
Ma'am, kindly take an example of by
Because
letting them explain. I am understanding by the graph, but not understanding by the matrix.
Which one are you not getting? Which question? Which one is it? Someone had a query. Which part is it from? What's the query? If you won't respond, we'll have to end the session there.
Yeah. In the meantime, I had out whatever we saw that mark that we have it. Is it quite? Is it something only focused on 9011 or it's mark as per the interim thing?
Sorry, what?
The mock exam, the mock text that is
Yeah.
there, the final for the interim. I find it. Is it the way because like I felt it's more of a focus towards the last week compared to the one that was discussed. So it will be it is because it's the third mock, so it's been given like that, or it will be the same pattern like the interim. It's the same pattern for the interim also.
I'm not sure about this thing, but it's if it's the mock for the end term, then it is going to be of the same pattern, I guess.
Okay, thank you.
There are no doubts. We're wrapping up the session here. Okay. Thank you everyone for joining.
Thank you. Thank you.
Okay.
thank you, ma'am.
Hello, hello. Here, anyone can explain one question. I am sending in the chat.